recording. Okay. So today we will have the first lesson about an introduction to forecasting, and the next one will be a little bit more advanced about probabilistic forecasting. The lesson of today will last maximum 2 hours, and we will do a short break at the end of the first hour, 5–10 minutes. And after this lesson, we will do another break, 5–10 minutes. And after that, I will present you the forecasting assignment and to explain it to you, etc. And you could answer. I will answer question, whatever it is. And the next week we will do the next lesson, and after that we will do a session for question and answer about the forecasting assignment. So I will first share my screen to show you the slide. Okay. So you should see my slide, and I wanted to tell you something before. I will just. It is you have in Collaborate. You can ask the floor. There is a small guy at the bottom of your screen. So I am doing right now. So you see, I raise my hand. So like that, I can ask the floor. But you are only 8. So just if you have any question, just take the floor and ask the question. I think it will be more easier to raise the hand. Okay, if it's okay with you, we will do like that. So we come back to the presentation now. Okay. So first, can you see the presentation? If anyone can answer me. Yes. Okay. Thank you. Great. Thank you. And the slides are on the GitHub of Bertrand Cornelius. So you can download the slide on its GitHub. Okay. So this first lesson is about an introduction to forecasting. And the learning objectives are to understand the context of forecasting with an application to renewable energy, to produce deterministic forecasts, and to perform verification of deterministic forecasts. These are the objectives of the lesson of today. And we will go through first the forecasting context, then the potential sources of error due to for forecasting. Then we will introduce the deterministic forecast and the verification of deterministic forecast. These concepts, deterministic forecast and verification of deterministic forecast, will be of good use for the forecasting assignment. But first the context. So why forecasting? In fact, forecasting is a natural step for decision making. We could forecast just for forecasting, why not? But at the end, most of people, they use forecast for doing something, and most of the time it is for decision making. So believing we know what will happen will help us making decision, of course, and it will make us more confident about it. Most of the time, this is that, in fact. And the key area of forecasting are energy, finance, economics, weather, climate, etc. So in fact, in almost every sector, there are forecasts, and decision makers use these forecasts to take decisions and to be more confident about it. So this is something that is widely used. If we come back to the energy sector, because this is a topic of interest in this course, because we're in the microgrid lesson, and you have this sector, you have these actors. There are many the energy producer. It could be a coal power plant, a nuclear power plant, a wind power plant, PV plant, etc. They produce some energy. So in this sector, it is electricity. And then this electricity goes to the grid, so to the TSO and DSO. Then from the main grid, it goes to the residential consumers or industrial consumers, etc. You have also the energy suppliers. The energy suppliers, they provide you energy by making a contract. They can make a contract with an energy producer to buy energy from a producer, and then they can sell the energy to some consumers. or they can buy energy on the market. So they are also market operators. So it is to show you the main actors of the energy sector: the energy producer, the TSO or DSO that transport, distribute the electricity, the energy suppliers, the market operators, and the consumers. In fact, each participant will have a different need in terms of forecasting. For instance, the energy suppliers of the TSO or DSO, they like to have electric load forecast because they want to know in advance what will be the consumption. If they know in advance the consumption, it's easier for them to supply their clients or consumers. Energy suppliers and energy markets, for them it could be interesting to have, for instance, daily forecast of electricity prices. For the energy supplier, it is interesting to have this forecast because like that they know in advance how much of energy they could purchase and at which price. There are also the imbalance volume and prices forecast. It could be interesting for the energy supplier, TSO, DSO, but also the potential congestion on interconnector, because the TSO and DSO, they have to balance the grid. And if they know in advance the potential congestion, it's easier for them to balance the grid. The producer, for them, it could be interesting to know in advance what will be the generations of tomorrow. Because if they know in advance how much of energy they will produce, it's easier for them to adjust the contract or the price at which they will sell the electricity, etc., etc. And in fact, nearly all of these quantities are driven by weather and climate. So if we come back to the scheme with the different actors of the energy sector, it is interesting for the energy producer to optimize benefit from generation. The TSO and DSO, they have to balance the grid. The energy suppliers, they would like to optimize benefit by selling energy. The market operators, they would like to optimize transaction. And if we focus on the consumers, for industrial consumers, so large consumer, they want to optimize their consumption. But if we focus on residential consumer, it could be the same. So we are residential consumer. I have an energy contract with an energy supplier. And if it is possible, I would like to optimize my consumption. So each of these actors, they want to optimize something. So they want to make a decision. And to make a decision, it's easier if you have a lot of information. So each of these actors, they would like to have some forecast of something to help them to make a decision and to optimize something. So this is why forecast information is widely used as input to several decision-making problems in the energy sector. So for instance, for the definition of reserve requirements, that is the backup capacity for the system operator. So system operator is the TSO. And if it knows in advance how much of reserve it will have, it's easier for him to balance the system. It is of good use also for unit commitment and economic dispatch, coordination of renewables with storage, design of optimal trading strategy, electricity market clearing, optimal maintenance planning, etc., etc., etc. These are just some examples, but you have a lot of other applications. So the forecasts are input to this decision making, and there are several methods to produce this forecast. You have the deterministic forecast. You have also probabilistic forecast as quantiles and intervals. That will be the next lesson. But you have also probabilistic forecast in the form of trajectories, or sometimes there are named also scenarios or risk indices. Here on the lesson of today, we are only focusing on deterministic forecasts. And the next lesson will focus on probabilistic forecasts as quantiles and intervals. And we will not see the probabilistic forecast in the form of trajectory on the last one. This is a microgrid reminder. So the EMS, Energy Management System, optimizes the decision based on what? Based on monitoring that provides some data of the system, observation of the system, and also on forecasting. So for instance, on this microgrid here, you have a genset. You have also a wind turbine or a PV plant. You have also a storage system and a load. And the EMS is trying to optimize the decision of all of these devices based on the monitoring and the forecasting. So the the monitoring, it pulls and stores data. Then based on this monitoring, it can help to make some forecasts, for instance, of consumption and generation. These forecasts are used as inputs of an operational planning to take decision for the next day, for instance, on the energy market participation. But also, the operational planning will be used as input of the real-time controller. The real-time controller takes decision for the next second. If we look at the EMS timeline, for instance, here you have the forecasting module that is in blue. It produces some forecasts, for instance, each 15 minutes. These forecasts are used for the operational planning module that compute a planning each 15 minutes. And you have in red the real-time optimization module that compute a decision in real time, for instance, each minute, and that use the operational planning as input. So the microgrid key parameters to forecast are vast. For instance, for generation, it could be PV, wind power, hydraulic power, etc. For the consumption, it can be the load of an office, of an industrial, residential, etc. It depends on your microgrid. And for the prices, it depends also of the microgrid, but mainly it is electricity or gas prices, and on different time scales. So for instance, future prices, day ahead, intraday, and imbalances. Do you have any question at this stage?
Yes.
Yes.
At the previous slide, I don't really get the difference between forecasting and operational planning.
So this one?
Yes.
Okay. The forecasting is used as inputs for operational planning. The operational planning is in fact the decision-making module. And to make a decision, it bases its decision on forecasts. So it uses forecasts as inputs for decision-making. So that's why the forecast has to be done before the operational planning.
Okay.
Is it better like that? Did you get it?
Yes. Yes.
So imagine, for instance, you have a microgrid and with a PV plant. And so the forecasting module will produce some forecast of the PV generation, for instance, for the next 15 minutes. So it says, okay, I estimate that the production will be something like that for the next 15 minutes. Then the operational planning takes that information as input, and based on that decision, say, okay, it seems that for the next 15 minutes, I will have a nice production. I will have a lot of PV generation. So, okay, nice. So based on that, okay, I can say that I can charge my battery storage, for instance, because I estimate that I will have a lot of PV generation. So that could be something like that. But it could be also something like the forecasting module computes a forecast that says, no, for the next 15 minutes, we will have almost no PV generation. So the operational planning module takes that as input and it says, okay, I cannot charge my battery, but I need some energy for my loads, but I will not have PV generation. So okay, I will import from the grid some electricity, for instance. Okay.
Okay. Thank you.
You're welcome. Do you have any other question? No?
No.
Okay. So let's go through now the potential sources of error about forecasting. And I think after that, we will make a short break. Okay. Okay. So what are the main contributions to forecast uncertainty or error? So when we are considering renewable energy forecast in the electricity market, most of the time, the forecasting module uses some inputs to make the prediction, and most of the time it uses recent power generation measurements that comes from the monitoring, and it uses also the weather forecast, and possibly sometimes extra information, so for instance radar images or whatever. But most of the time it is mainly about recent observation and weather forecast. So imagine a PV plant. You would like to forecast the PV generation for the next hour, for instance. So what you need to know to forecast this PV generation is the weather prediction of the solar irradiance, because the PV generation is mainly driven by the solar irradiance. Okay, so you will try to have some weather forecast of the solar irradiance. But it could be interesting also to have the last measurements of these PV plants. So for instance, the PV generations of the last 15 minutes. Okay, and so like that, you can combine these two information and try to make a forecast of PV generation. So the importance of which one you will use varies as a function of the lead time of interest. So for instance, if you want to compute very short-term forecasts, so from now up to 6 hours, we definitely need some measurements because the weather forecasts are not very accurate. They cannot tell you, okay, probably in the next minute you will have a cloud, for instance. The weather forecast, it's more like an average. So it will tell you, for instance, about the solar irradiance. Okay, on average, for the next hour, you will have this level of solar irradiance. But it will not tell you, okay, you have this amount of solar irradiance for each minute of the next hour. It's more like an average. So if you have some measurements, with the measurements, it will tell you, okay, right now I have a cloud, and it is coming above my PV panel, and probably it will go through my PV panel. There has been a question. Oh no, okay, sorry.
No, it's me, just disturbing you.
I was hearing something, but I cannot see the little guy when I share the screen. Okay, great. And so in the short term, you definitely need measurements to help to make the forecast. And if you are considering a more early medium range, like from 6 hours up to 1 day, weather forecasts are a must-have. You cannot avoid weather forecasts. And so here on this graph, you can see on the y-axis, the error of the forecast, and on the x-axis, the lead time. The lead time is a forecasting horizon. So for instance, you could say, I would like to forecast the PV generation for the next day. So if you want to forecast the PV generation for the next day, the horizon, the forecasting horizon is 1 day. But it could be 2 days, 1 week, 6 hours, 2 hours, 1 hour, etc. And so this graph tells you that the importance of the weather forecast and on the measurement, and on the error of the forecast. And so the smaller the forecasting the horizon is, the higher the error is due to the measurements, because the measurements are the features that help the most to produce the forecast. And then it is the weather forecast. It is important to understand that, because it will tell you, in fact, where does come from probably your error forecast. So if you are forecasting on the very short term, you will try to improve your measurements. And if you are trying to forecast on the medium range, for instance, you will try to improve your weather forecast to decrease the forecast error. So to show you some weather forecast, I have some little noise. Antoine, yes?
Regarding the error made on the measurement, I don't understand how can an error be on the measurement?
when you measure something, it is not the ground truth, no?
Okay.
So imagine you want to measure the temperature, the air temperature, for instance, because the air temperature will have an impact on the PV generation. And so depending on what is the device, you will not have the same measurement, and you will have an error with that measurement. So there is no perfect measure. There is no perfect observation.
But the error made on the measurement should be relatively small regarding the error made on the meteorological forecast.
It depends, in fact. If you want to forecast the PV generations for the next hour, it is a very short-term PV forecast. So you would like to have very accurate measurements in comparison with weather forecast, because you know that the weather forecast for the next hours does not have a very deep impact. So it's better to focus on the reduction of the error on the measurements. It is okay. Is there any question? No. Okay. Oh. Okay. So mainly for forecasting, we use measurements and weather forecast. Here to give you an example of weather forecast, we have at Liège, at the Laboratory of Climatology of Liège, Xavier Fedweiss, that uses a forecasting model, a weather forecasting model. And on its website, so I am going to its website, you can see the weather forecast. So here, so for instance, for Belgium. Okay. And there are some graphs. And here, for instance, you have the air temperature at 2 meters from the ground on the entire Belgium. And it is refreshed, I think it is every hour. So here you have the date. And you can see like that the weather forecast for the air temperature on Belgium. And so it is a weather forecasting model that is running all the time. And he put its forecast on this website, and you can have free access to it. So here you have the temperature. But there is also other things. So for instance, I come back. You have that. So let's say that we are at the Sartilman, for instance. You have several locations. So here are the Sartilmans. So you have here the forecast for the temperature here in red. From now up to here, the forecasting horizon is of 10 days. Because you see that you have a weather forecast for the next 10 days. And so you can see the air temperature here in red. In degree, you have also the wind speed. You have the solar irradiation. So here we can see that it is a very beautiful day. Yes. But tomorrow it will be a little bit more cloudy. But it seems that on Sunday it should be a nice day. You have also the precipitation. So liquid, it is when it is raining. And there is no snow here. So the snow height is 0. So this is a weather forecasting model, and it is running all the time on the entire Belgium. And we use, in fact, these weather forecasts for PV generation forecasting, for instance. And it is quite a nice model. Okay, so let's take, for instance, a wind power curve for a specific wind turbine. And probably you know that the power of a wind turbine is completely related to the wind speed. And here is a theoretical wind power curve. So when you have no speed, of course, you have 0 for the generation. And when the wind speed is increasing, the power is increasing, but it is not linear. In fact, it is related to the cube of the wind speed, and then up to a certain threshold or limit. And then after a threshold, the power is 0, because if the wind speed is too high, it risks to destroy, in fact, the turbine. So this is like that. So this is a theoretical power curve of the turbine. And in fact, a large part of the prediction error directly comes from the prediction of the weather variables. Because imagine that your forecast of the wind is 12 meters per second. So if it is 12, it should be this amount of power. So approximately 500 kilowatts. But it is a forecast. But imagine, in fact, the realization is not 12, but 10. If it is 10, it is not 500 kilowatts, it is more like 400 kilowatts. So you make an error of 2 meters per second that results in an error of 100 kilowatts. If, for instance, we are here between 0 and 4, if you forecast 4 or 2, the generation is 0, so it will have a 0 impact. So the meteorological forecast is then amplified or dampened by the power curve of the model. So here it is for a wind turbine. And there is something else here. So it is a theoretical power curve, but the actual wind power curve is different. And in reality, it is more something like that. So you can see that for the same wind speed, you will not have always the same power, because it does not depend only on the wind speed. It depends also on other factors. So even if you have a perfect prediction of the wind speed, in reality, the actual generation will be a little bit different. So that's why it is very hard to forecast, because you need very accurate weather forecast, and even with very accurate weather forecast, you will not have the perfect actual power. Okay. Do you have any question?
No.
No? Because if you don't have any question, we can make a short break. If you are okay, like 5 or 10 minutes, I don't know what you want. Do you want a break or not?
For me, not necessary, but it's the same.
Okay. 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 And as Bertrand told you, if you want, you can also ask question in the chat. There is also a chat, so okay, you can also ask question there. But so if you are okay with no break, we can keep on going. Okay, so let's keep on going. Okay, so I will share again my screen. Okay. So we have been talking about the forecasting context, the potential sources of error. Now we will focus on deterministic forecasts. So the practical setup is we are at time t. For instance, it could be 11 a.m. And we are interested in knowing what will happen at a time t plus k. So it could be, for instance, 12, 13, etc. The index k, is referred to as the lead time, so the forecasting horizon. And so we are at time t, so we have some knowledge of the observation of the stochastic process up to time t, and after time t, it is the future, and we would like to forecast in the future. So for instance, at time t plus k. And this is a random variable. So the power generation is a random variable, and we would like to predict it. So what will be at time t plus k? Will it be more, less, etc.? And the forecast is an estimate for time t plus k, conditional to information up to time t. So we use all the information that we have up to time t to try to estimate what will happen for time t plus k. So this is a forecast. A forecast is an estimate, conditional to some information. And the point forecast informs of the conditional expectation of power generation, because it is a stochastic process. And the point forecast, it is one value. So where a point forecast, it is just one value for a specific lead time in the future. So for instance, for PV generation, it is a level of generation, but it is a value. It is, for instance, 100 kilowatt at 1 p.m., 200 kilowatt at 2 p.m., and etc. This is just one point. And so a point forecast is a conditional expectation of power generation. So you take the expectation of the random variable, conditional to some information that you know at time t. And so this is denoted by the information set omega. So the information set, it is what in practice? It is a weather forecast, for instance, but it is also the past observation or other information that could be of some interest. For instance, if you know that you will make a maintenance on your wind turbine, definitely you will use it, because if you know that in 2 hours you will make a maintenance, you know that there will be no generation. So the information set omega is every knowledge that you have about the stochastic process up to time t. Then it is conditional to a model J. So you will use a model to make some forecast, and we will see after what could be this model. And its estimated parameters. The model will have some parameters that you will try to estimate. So when you are trying to perform a point forecast, you are trying to compute a point based on some informations on a model and its estimated parameter. Do you have any question about what is a point forecast? Because it is important to understand that. No question? I will just check the chat. Okay. So the point forecast is an expectation of the stochastic process given an information set, a model J, and its estimated parameter at time t. What could be J? It could be a machine learning models, such as neural network, gradient boosting, etc. But it can be also a parametric model. So for instance, for PV generation, we know that the PV generation is directly related to the irradiance, the solar irradiance, big A, and the air temperature. And we know the law, and it is this one. So we could use this parametric law. And here you can see that the estimated parameter have to be A, B, and C, and you have to estimate this parameter given your PV plant. But it can be also a statistical model such as ARIMA, etc. So G could be anything. You have a lot of different kind of model, from machine learning model to parametric to statistical model. So let's take an example. So for instance, it is some point forecast for PV generation. In red, you have the observation, so the PV observations, and in black, you have a day-ahead forecast. A day-ahead forecast means that you have computed the forecast 1 day before the observation. So for instance, here, the PV point forecast in black were computed at 12 for the next day. And the time discretization is 15 minutes, so you have 96 points per day. But here, as during night hours you have no productions, we just plotted the PV generations between the lead time 10 and 80. So around like 3 a.m. up to yes 8 p.m. And if you want to have more detail, you have here the reference of the paper. And so you can see that, and another information, the model here is a neural network, a feed-forward neural network. And it is just to show you how it looks like. It looks like, sorry. And so you have 2 different days. And the first one on the left is is a day that is not really sunny, but that is cloudy, but not too cloudy. So you have the PV observation fluctuates a lot. And you can see that there are some difference between the forecast and the realization. And on the right, you have a sunny day. Not a perfect sunny day, but almost, because you have a very nice production curve. And you can see that the point forecast is more close to the realization. And of course, you can understand that it's harder to forecast PV generation when the day is not completely cloudy and not completely sunny, because it is very difficult to anticipate clouds. So if you know in advance, based on weather forecast, that it will be a completely cloudy day, you know that your PV generation will be almost always 0, so it's quite easy to know. If you know in advance that the day will be sunny, completely sunny, it's quite easy to forecast. But if you don't know really, so you are between cloudy day and a sunny day, it's much more difficult to forecast PV generation. And this is what is happening on the left picture. Okay. So you can forecast, you can in fact classify forecast into 2 dimensions. You have the first dimension that is the time. So based on the forecasting horizon. So you will not use the same model for doing very short-term forecasting. So from a few minutes to day, for short-term forecasting from day to week, from middle-term forecasting from week to years, and long-term forecasting. So you try to forecast, for instance, the PV generation in 3 years. You have also the forecasting resolutions, because you can use discretization, time discretization of 1 minute, 10 minutes, 15 minutes, 1 hour, 2 days, 10 years, etc. So this is the first dimension, and you will not use the same model. So you have some models that are very accurate and very good for very short-term forecasting. Some others very accurate and very good for short-term forecasting. And on the second dimension, that is a spatial dimension, the spatial forecasting horizon, it is not the same thing to try to forecast the PV generation of microgrids, a very small microgrids, or of all the PV generation of Belgium, for instance. It is not the same thing to do. And so depending on the dimension, and when you are on this classification, you will not use the same model. So for instance, when you are considering very short-term forecasting, it will be related to demand response or for hour-rate scheduling, etc. When it is short-term forecasting, so from 1 day to 2 days up to 1 week, it is more used for unit commitment or energy trading. And when you are trying to forecast the energy generation or consumptions with a forecasting horizon of 1 year, 2 year, 3 year, it is more used for system planning. And then if you want to forecast the consumptions or generations in the next decade or in 20 years, 30 years, it is more used for energy policy. So using a forecasting model depends completely on what is the applications. If you want to do unit commitment or system planning or energy policy, you are not focusing on the same forecasting horizons, and so you will not use the same models. You will try to take the model that is the most relevant depending on your application, and consequently for the decision making you want to do. Okay, so now let's say that you have decided what will be the application. So imagine that, for instance, we are considering a small microgrid that is composed of a load, a residential load, for instance, a PV plant, and a battery energy storage device. So you know that you want to forecast PV generation, but what are the forecasting predictors? The predictors are the information that you want to use for your forecasting model. So if you want to perform PV forecasts, Of course, you will use solar irradiation forecast, but also air temperature forecast. So you will use weather variables. But it could be something else. So if you want, for instance, to perform forecast of the consumptions, probably you will use calendar variables, because most of the time the consumptions is related to the days of the week. For instance, for the consumptions of offices, people, they go to office most of the time from Monday to Friday. Of course, when we are not in the COVID situation, imagine a normal situation. So most of the time, people, they go to the office from Monday to Friday, and they work from Monday to Friday. And during the weekend, most of the people are at home. So the consumption is different between the days of the week and the weekend. So you can use calendar variables, etc. So depending on what you want to forecast and what is the forecasting horizon, you will use some information or not. So it completely depends on the forecasting problem, in fact, you want to address. And this is very important to understand, because if you want to produce accurate forecast, you need to select carefully the forecasting predictor, because the model in itself can do nothing without informations. And so if you want that your forecasting model produce relevant and accurate forecast, you need to feed him with relevant informations. So if you want to try to forecast PV generations, and if you give the model as inputs the forecast of the, for instance, of the electricity market prices, of course it will not work. You need, for accurate PV generation forecast, to feed your model with solar irradiations, temperature forecast. So for instance, if we come back to the last example, for PV solar generation, for PV generation forecast, the predictors that are used for the neural network here are the weather forecast of the solar irradiation and the air temperature. And they both come from the weather forecast model of the Laboratory of Climatology of Liège. Okay. So we have seen what are the deterministic forecasts. Do you have any question about it? If you don't have any question, we can go now to the topic of the verification of deterministic forecasts. So let's take a case study. So the PV parking rooftops from Liège University. So you probably know that on the parking rooftops there are solar panels, and it is quite a nice installation because there is 466.4 kilowatt of PV installed capacity. And here you have the link on the description of the PV panel. And so we will take this data. So we use this data, the observation of this PV panel, and we use as a forecasting model G, a feed-forward neural network. We use it with one hidden layers. We use as a predictor the weather forecast of the solar irradiation and air temperature. The output layer of the neural network is composed of 96 neurons because we are trying to forecast the PV generation for the next day. And the next day is discretized with a time resolution of 15 minutes. So you have 96 quarters in a day. So you want to produce 96 points of PV generation. And it is implemented in Python using TensorFlow library. But so how do you evaluate the forecasts that are performed by this model? Forecasting is about being able to predict future events. And okay, great. But then how can you evaluate that? Because you need, in fact, to verify forecasts on data that has not been used for the modeling. Because if I come back to this model, so I will check that neural network, I will fit it on some data. So I will use weather forecast, and I will try to fit my model on observations. So okay, great. But how can I evaluate that model? I cannot take the same data that I use to fit this neural network. So you need data that has not been used for the modeling. So there are several strategies to do that. First, you can split your data set into two parts, a learning part and a validation part. So here on the left picture. So you keep some data for the training, you use it just for the training, and then you make forecasts on the validation part and you compute some metrics. Or there is also a second strategy that is named K-cross validations. So you compute K pairs of random learning and validation sets. So for instance, you can divide here your data set into 10 parts. So you have 10 parts, and you use randomly 9 parts for the learning part and 1 part for the validation set. So you do it like that the first time, and then the second time you take another 9 parts randomly, and etc. And so you can do this like that 10 times, and so you will have 10 pairs of random learning and validation sets. So the K-cross validation is quite nice because with the same data set, you will generate much more validation sets than the first one. But then each methodology has its own pros and cons. Yes, Juliette?
Just so you know, we haven't had any machine learning course, so as far as I'm concerned, I don't really know what is the learning set and then the validation set, although I can maybe understand that we make forecasts and then we see for the validation step if it's well done or not, or...
It is exactly that, in fact. So you have your data set. For instance, imagine you have 1 year of data. So imagine here for the PV rooftop of Liège University, we have 1 year of data. So we measured the PV generation of the PV parking rooftops for 1 year. So we have 1 year with the observation, okay? And I have also 1 year of weather forecast. So I store this data, and I have one year of weather forecast of the solar irradiance and the air temperature, and 1 year of realization of the PV parking rooftop. Okay, so I have 1 year. This is my data set. Okay, and so the idea is I take a model, a forecasting model. So here it is a neural network, but it could be whatever you want, a model, just a model. And you need to fit the parameter of the models. And you have 1 year of data. But if you take the entire data set, so the 1 year, and you fit your parameter, okay, great, you have fitted your parameter of the model, but how can you now evaluate the model? Because you cannot evaluate the model on the learning set. It's impossible. So you need to divide your data set into 2 parts. The first part, that is a training set, and this is, you take some data. So for instance, imagine you have 1 year, you take 8 months. You take 8 months randomly, and you use these 8 months for estimating the parameters of your model. And then you have left 4 months where you can evaluate your forecast. You use your model that now has been, its parameter is estimated. You produce a forecast on the other 4 months, and you compare to the realization. Yes?
So sorry, Jonathan, just to complement a bit your explanation. Actually, indeed, you didn't have a lecture about course about machine learning. The idea is to give you the basics in this lecture and to try to go hands-on directly. Maybe to complement a bit what Jonathan is saying is that actually it's a bit difficult to introduce this notion in a few words, but you could actually evaluate your model on the learning set. But if you do that, you will there will be a bias of evaluation, basically, because if you want to evaluate your model on the it's always easy if your model is powerful enough to have a model that is perfect on the learning set. If you have many parameters, there is always one or several values of these parameters that will give you almost 0 error if you evaluate your model on the learning set. But that doesn't mean that if you do that, it's going to be a good model for making some forecasts. And actually, in machine learning theory, it's even the opposite. When you do that, you do what's called overfitting. You overfit your model on your data. So this is why as Jonathan said a bit, I mean, of course, it's difficult to explain, but a bit quickly, you cannot evaluate your model on your training set or learning set. So you have to divide your model in a training set and a validation set. And the validation set is not used for, of course, not used for training. It's just used for evaluation. So this is just, of course, we can come back to that later on if you, during your assignment, if you want to explain it a bit better. But this is, it's not very difficult to understand, but of course, maybe it goes a bit fast here.
Yes, yes, I took a shortcut here. When I say that it's you cannot take the learning set for evaluation, you can take it, of course, but as told Bertrand, it is there will be a bias. And you can imagine also when you just take another lesson. So, for instance, you try, I don't know, imagine you are doing some math, and you work very hard for your exam, and you learn a lot of things, but always the same type of exercise, always the same methodology. And for the exam, it is something different. So you spend weeks and weeks of homeworking on a specific methodology, and you completely forget about something else. So you go to the exam, and in fact, you cannot do anything but just what you just learned. And this is the overfitting. Sometimes it is nice to learn, but if you learn too much the same thing, it's difficult to adapt to other things. And the idea of a machine learning model is to try to find a trade-off between learning and adaptation. So you need to learn to do something, but if you learn too much on the same thing, it's difficult to adapt. So that's why you have to find a trade-off between overfitting and underfitting. But we will come back to these notions during the forecasting assignment. I think it will be easier for you to understand. Here, what you have to keep in mind is that it's better to evaluate a model to have a training part and a validation part. And you can do it on with several strategies. You can just divide like that your data set between a training and validation part, or you can use k-cross validations, where you compute several pairs of random learning and validation sets. Okay. Okay. So we just say that we would like to evaluate some forecasts on a validation set. Okay, it's nice, but how can we evaluate the forecast? What does that mean? Evaluation, in fact, for forecast. So it can be visual inspection. So visual inspection, allows to develop substantial insight on forecast quality, and it's nice to have a look at the forecast, just to have a look at the shape. And but it is just a qualitative analysis. It is not quantitative. So you cannot just use visual inspections, but it can help just to have a first look at the forecast and to know if the model is nice or completely bad. So for instance, here you have 2-point forecast of PV generation. So it's the same case study of the PV rooftop of Liège University with the neural network. So on the left part, it is a point forecast issued on the April 3rd at 12 for the next day, so for the 4th of April. And on the right, it is a forecast issued on the May 4th for the May 5th. So in red, it is the observation, and in black, it is a point forecast. So what do you think of these two? Are they good or are they bad? Just like that, tell me.
It seems like the second one is better.
So the one, yes, on the right part, it seems it's better. And when you say it seems, what does that mean?
Because I guess it's maybe not the right answer because you're gonna give more explanation.
No, it's a good answer. Don't worry. Just explain it to me and to the other students. Why for
yeah,
you
because it seems to fit the. Yeah, well, the forecast seems to fit the observation.
Yes, just like that, huh? Yes. When we look at it just like that, it seems that the black and red curve are much more closer for all the lead times on the right picture than on the left one. It is just that, huh? Yes. So for me, and I completely agree with you, sorry, it seems that the right one is better than the left one. Just like that, it seems, huh? There is no problem at all, I agree with you. And so we could say that our model for the left part, because it's the same model, huh? It's just 2 different days of the validation set. So it seems that the model that we use, this neural network, and for the 4th April, did not perform well, but for the other day, it performed better. Yes, we can just say that. Okay, so this is one way to evaluate the forecast. So you take your validation set and you just have a look at the forecast for all the day of the validation set. And if, imagine you have 100 days in your validation set, you have a look on 100 days, so it's a lot, huh? But imagine you do it. And among these 100 days of the validation set, let's just say that we have 90 days like the day on the right and 10 days like on the left. We could say that, okay, our model is not so bad because for 90 days of the 100 days of the validation set, the forecast seems nice, okay. So this is one way to do it. And I encourage you to have a look at the forecast just to have the first insight. Okay, what can we do now? We still have a look on the forecast, and in fact, the errors are most often driven by weather forecast error. So there are some typical errors for PV generation. So for instance, these are first amplitude error. So this is the error on the left. It seems the shape and the phase is quite nice, but the forecasting model that is in black underestimate the generation in comparison with the realization. And so this is typically an error that is named amplitude error. So the model made an error of amplitude, even if the shape is nice. But it could be something else different. It could be a phase error. So here on the right, it is a typical phase error. So the shape is not so bad. The amplitude is not so bad, but you can see that there is a phase error. It is a little bit shifted in time. So, and most of the time, these amplitude and phase errors are driven by weather forecast error. So probably, for instance, for the left figure, that the solar weather forecast was a little bit smaller than the realization. And so the model used this weather forecast to produce the PV generation and made consequently an error on the amplitude because of the error on the weather forecast. So most of the time it is something like that. But you cannot do anything about it because you use weather forecast as inputs. So if your model is quite well fitted, imagine you have a good model. If the weather forecasts are bad, the resulting forecast will be bad. You cannot do anything about it. It is like that. Or maybe you can just change of weather forecast. But most of the time, it's not so easy. Okay. So we discussed about qualitative ways of evaluating weather forecasts, so just visual inspection. But it is not enough. It just provides an insight. But most of the times, what you need to do is to use quantitative metric. So this is a quantitative analysis. So you can define the forecast error like that. That is the epsilon. So you just take the true realization minus the forecast. This is the error. Okay. So you compute the error for each time step. And then you can normalize it, for instance, by dividing this error by the nominal capacity. Like that, you will have something that is expressed in percentage. Okay, so when you do that, you just compute the forecasting error. So let's take an example on a wind farm with a normalized error. On the left figure, you have the observation of the forecast. So here, for instance, typically you have a phase error between the forecast and the realization. And then on the right, it is a computed normalized forecasting error. So you can see that for the first lead time that are here expressed in error. So for the first 18 hours, the normalized forecasting error is quite small. and it corresponds to the graph on the left because there is not so much differences between the observations and forecast. But between the 18 hours and 25 hours, the forecasting error is increasing, and that corresponds to the phase error. And then it comes back more to a smaller error. So this is one way of doing a quantitative analysis. So you can just plot the normalized forecasting error for each lead time. And then you can compute scores that are used to summarize aspects of the forecast accuracy. And there are a lot of quantitative metrics, but the most common scores are the bias. So the bias is what it is just, in fact, the average over all the forecasting periods of the forecasting error. So you just make the average. This is a bias. You can compute the mean absolute error or the normalized mean absolute error for the normalized versions. That is, in fact, the average of the absolute of the forecasting error over all forecasting period. And you can also compute the root mean square error. That is the average of the square of the error. Okay. And so most of the time, it is quite sufficient to compute these quantitative metrics. It provides you a nice information about the forecast accuracy. So let's take an example. We'll come back to the case study. So here we have three forecasting models. The blue one, MLP, is a neural network. The red one, LSTM, is another kind of neural network that is different. And the green one is another machine learning technique that is named gradient boosting regressor. But as you did not follow a machine learning lesson, I will not go into the detail of this machine learning model. Just keep in mind that there are three different machine learning models, okay? And so the plain lines are the normalized mean square error, and the dashed lines are the normalized root mean square error. And we perform the evaluation of these metrics by using a k-cross validations. And here k is equal to 11. It means that we computed 11 pairs of learning and validation set. So we had 11 validation sets, and we average each score over the 11 validation set. And so we can compute these metrics, the normalized mean square error and the normalized root mean square error, per lead time. So for each lead time of the day. So here it is for each quarter of the day. And so you can see that for this matrix, so for instance, the normalized mean square error, the best model is the red one, the ELSTM, sorry. And then it is the MLP and then the GBR. And that the error here that is expressed in percentage of the total installed capacity is much more higher during at lunchtime than at night hours. But it is completely logic because when do you have PV generation? When the sun is high in the sky, of course, so at lunchtime. So when you are doing forecasts, this is where you will make most of the errors. And expressed in percentage of the PV total installed capacity, the error will be much more higher at lunchtime than in the morning or at the end of the day. Does it make sense for you? Do you understand, in fact, this plot?
Mm-hmm.
Yes? Okay. Okay, so I will not talk more about the metric. So I will conclude these first lessons about the introduction to forecasting. So we forecast for doing something. We do not forecast just for forecasting, just not for fun. Forecasting is a natural step for decision making. And the key parameter to forecast for a microgrid are, for instance, the PV generation if you have a PV plant into your microgrid. It could be a wind power, etc. If you have into your microgrid an office, industrial loads, you will want to forecast it. Maybe you want to forecast the electricity prices or the gas prices if you want to bid on some energy market, etc. but you forecast for decision making. You do not forecast just for forecasting. So this, you have to keep that in mind. What is a point forecast? What you have to keep in mind is that a forecast, it is an estimate of something, a random process. So for instance, PV generation, but it is an estimation. It is not the ground truth. It is just an estimation. And you try to estimate something. So for instance, the PV generation at time t in the future. So for time t plus k. And you use the knowledge that you have up to time t to try to estimate this process in the future. So that's why it is an estimate conditional to some information. And the point forecast, so deterministic forecasting, it is a point forecast. It is when you perform a conditional expectation of the random process. So you are trying to compute a point in the future. This is a point forecast. And in fact, it is the expectation of the random process. And to do that, you use a model G. That can be a machine learning model, but it can be something else. It is a model. You use an information, so weather forecast, measurements, and based on this information, so the realization, the weather forecast, etc., you try to estimate the parameters of your model. And once you think that your parameters are well estimated, you try to evaluate your model on a validation set. And so you have several strategies to assess forecast. Most of the time, you can just split your data set into two parts. You keep one part for learning. You estimate the model, the parameter of the model. Wait a minute. Yes. Ouais. No, c'est okay. It's okay. Sorry. We thought we have been disconnected, but it's okay. And so you can split the data set into two parts, a learning part and a validation set. You estimate the parameter of the model on the training part. And once you think your parameters are well estimated, you try to estimate the forecast on the validation part. Or you can use another strategy that is named K-cross validations, where in fact you will divide your data set into a learning part and validation set, but you can do it randomly. And so you can compute random pairs of validation set and learning set. To assess the forecast, you can perform a visual inspection. So you just plot your forecast in comparison with the observation, and you just have a look at it and you try to estimate visually if they are well or not. And you can do a quantitative analysis by using quantitative metrics. And most of the time we use the bias, the mean absolute error, and the root mean square error. And it is better to use a normalized version to express the error as a percentage. If you want to dig deeper, here are some references, and I base this lesson on these references. Yes?
Can you explain the K-cross validation, please? I didn't get it very well.
Okay. Yes, of course. So imagine you have a data set with 1 year of data. 1 year of data of PV generation. So here for the PV Liège rooftop, and 1 year of weather prediction. Okay. So the first methodology, it is on the left part. You just divide your data set into a training part and a validation part. So for instance, 8 months for training and the other 4 months for validation. Okay. This is the first strategy. The second strategy, K cross validation. So imagine K is equal to 10. Let's fix K to 10. So you divide this data set into 10 parts. So here you can see some lines. So imagine the data set has been divided into 10 parts, okay? And so you have divided your data set into 10 parts. These parts are fixed. But you will select randomly which part is the validation or the training randomly. And so, sorry. Here, for instance, the validation set is in purple. So you select randomly one part among these 10 parts that will be the validation set. So for instance, it is this one. And so the other 9 parts will be the learning set for this configuration. And now you fit your model and you validate it on this part. Okay, so you do it the first time like that. Okay, so you did it. And now the second time you say, okay, I will take now another part as the validation set. So I select randomly another part as a validation set. So for instance, let's say this one. And you take the other 9 parts as validation set, and you perform your assessment, and so on and so on, so on. And so you can do it 10 times because you had divided your data set into 10 parts. So you can take the first part as a validation set, the other 9 parts as a learning set, and etc. So you can do it like that 10 times. And so virtually, it enables you to compute 10 pairs of random and of random learning and validation sets. So by using this methodology, it's like virtually you can expand your validation set because you computed 10 different validation sets.
Okay, thank you.
Is it okay like that?
Yes, thank you.
Okay. Juliette?
And then the idea is if the estimation is not well validated, then the parameters are changed when performing a
Each
new
time. Yes. Yeah, keep on going.
No, but if we take randomly one part and then it's not really validated because the parameters were badly chosen, then we change the parameters and we perform it 10 more times, or
in fact each time, so you have divided your data set into 10 parts. You take 9 parts for the validation set, so you combine 9 parts. Here the green one for a learning set. So you aggregate 9 parts for the learning set, and you just keep 1 part for the validation set. So when you aggregate your 9 parts here, you have 90% of the data set that is used for the estimation of the parameter of the model. So you estimate the parameter on the green part, and then you assess your model on the validation part. And then, okay, so this is the first step. And then in the second step, you pick randomly another part for being the validation set. But so it means that you have now another learning set. And now you re-estimate your parameter. So
and then we make the average of all parameters we have.
At the end, not of the parameter. So in fact, you produce some forecast. So at the first step, you estimate the parameter of the model on 90% of the data set. You compute forecast on the last validation set here. So you store the forecast, you keep it, you store it, okay. And then on the second step, you select another validation set. So and then you re-estimate again the model parameters. You produce the forecast on the validation set, etc., and so on. So at the end, you have 10 sets with forecasts. You combine them and you compute the score on it. It's like averaging the score over 10 pairs. But each time, the model will have different parameters.
Okay.
It's not the same model. It is the same model. It is, for instance, a neural network or whatever, but its parameters have been fitted on different learning sets. So it will compute differently. It will not be the same parameter. But so that's why at the end we average a score. But like that, virtually, it is like we had tested the model on the entire data set. It's a way of expanding the validation set.
So, excuse me, it's really a way to see if the model is good or not, and it's not to make a model.
Yes, the model is already implemented. So you, for instance, you select a neural network or I don't know, parametric model. You take a model and you want to assess the model. It is a way to assess the model. It is a validation.
I think it was the thing I had not understand. Okay.
Yannick?
If I understand it well, so the goal is to use this where you are expecting actually the data to look the same in the following year. Then, if you're trying to assess the parameters to have a good forecast on one data set?
Can you repeat the question?
So here we are trying to assess the models so that it gives a good forecast for a given data set. But in practice, we are trying to use it to forecast for the future. So we are expecting the data to look the same in the future then, because this...
I understand the question. You cannot know what will happen in the future, of course. But imagine here we are trying to perform PV generation forecasting. Okay, you know how it looks like the PV generation curve. But so the more data you have, the easier it is to estimate the parameter of the model. And so imagine you have, for instance, 10 years of data. So of course, from one year to the other, the PV generation is not the same because you have a seasonality, and sometimes there is a year where on average there is more sun, and etc. But you can say that with 10 years of data, most of the time you will have what will happen in the next year. It will not be exactly the same, but you can say with a lot of confidence that most of the time your forecast will not be so bad.
Okay.
But most of the time you have 10 years of data, you just only have a few months or 1 year.
Okay, so it's really to try to find the good parameters so that it will make good forecast in the future then.
Yes. You try just to find the best trade-off, in fact, given the amount of data you have. You try to extract most of the information based on the data you have. So if you have only 6 months of data, imagine you want to perform PV generation forecast, and you have only the data of PV generation of the last winter. You just had that, the last winter. Of course, you fit your model on the last winter. Okay, great. So you estimate the parameter of your model on the last winter. And now you are trying to perform forecast, but during summer. Of course, there will be a problem because the PV generation is seasonal. It is completely different between winter and summer because the sun is different. So the model will be badly estimated.
Okay, yeah.
Maybe the model is good, but its parameters are bad because we only get data from winter. So it completely depends on the application you want, but that is why forecasting, when you are doing forecasting, you need to be smart in the way you select data. So for instance, if you are considering PV generation, it's better to have data of an entire year to take into account the seasonality. But for instance, if it is a wind power turbine, sometimes between winter and summer, there is not much difference. So sometimes you can use a few months of winter, it is okay for summer. So it completely depends on what you want to forecast. And depending on what you want to forecast, you will select carefully the data you want to estimate the model parameter.
Okay, thank you.
You're welcome. And then there was someone else. So I don't know who was the first between Antoine and Charlotte. So if you remember who was the first to raise the hand, just take the floor.
I think it was me.
Okay.
Regarding what you said to Juliette, so we have 10 pairs of random learning and validation set on 1 year, but it is a different way to do it that way. Otherwise, we would have an overfitted parameters. That's right.
Can you repeat again so that I can be sure to understand your question?
So the method you said while using 10 different pairs of random learning and validation set during 1 year, and we have 10 different pairs of random on this year, but at the end we would have trained it on the whole year. That way the parameters are not overfitted. That's what we want to try to avoid.
It depends. In fact, here it is just an example to say we could divide the dataset into 10 parts, and so to fit the model on 90% of the dataset. But it will not tell you if the model is overestimated or underestimated. You don't know that in advance. You will know it when you will do it and look at the score. But maybe it completely depends on the application. So and on the model. Some model, you don't need a lot of data to estimate the parameter. And for some other model, you need a lot of data. So it completely depends. So maybe for a given model, you just need one month of data, and it's okay, and it performs well. And maybe for another model, you need 12 months of data. So here it is just an example to illustrate the validation methodology. And so they divided the dataset into 10 parts, but it could have been into 5 parts or 3 parts, etc., or into 20 parts. But it will not tell you if you will overestimate or underestimate the parameter of your model. You don't know that in advance.
To be sure, what I wanted to know is that at the end, we would have made 10 different validation tests on the whole year, and we would have...
At the end, yes. At the end, it's like we had used the entire year as a validation set. Yes.
Yes, but doing it like that would then make the parameters overfitted. Otherwise,
yes.
we
okay. You mean if you had taken the entire year directly?
Yes.
Yes, sure.
Okay, yes, that's what I wanted to know.
Yeah. And imagine if we would have taken the entire year as a learning set, there will be no more validation set. So it would be a problem. So this is a smart way. The K-cross validation methodology is a smart way to expand in a way the validation set, in fact.
Yes. Okay, that's what I wanted to know. Thanks.
Okay. Sorry. Thanks. And so now, Charlotte.
Just to be sure, so with the example, with the K-cross validation, so we have 10 models with different parameters. We take the forecast information and we make the average of the 10 forecast information.
So, in fact, we don't have 10 models. Imagine it is the same model. It is the same one.
Same model with 10 variation.
Yes, 10 variation of the parameter. We estimate differently the parameters on 10 different learning sets, and we compute 10 different forecasts on 10 different validation sets. And at the end, we average a score. Yes.
Okay, thank you.
But imagine, because it is interesting to do that, because imagine we just do it one time. So you divide your dataset into 10 parts. You estimate the model parameter and you do a forecast. Okay, so you have a score for a validation set. But you just have a score for 1 month. By doing it 10 times, you will have probably 10 different scores, and it can help you to understand, okay, if I average my score over the 10 validation set, I will have an average score, but I can compute also a standard deviation. So it will help you to understand the error of your model, because you will know that on average you have this error, but you have also this standard deviation. Because the error depends also probably on the month, because maybe your model will be very good to forecast the PV generation, for instance, during summer, and maybe it will be very bad during winter. You don't know it in advance. It completely depends on your model. Some models are very good for winter, some other summer, etc., etc. So it also provides you some information about how is the error of your model. So that's why it's nice sometimes to use K-cross validation.
Yes, and so it allows to conclude which parameters are better for this month or this month.
Maybe, and maybe sometimes you will use the same model. So for instance, a neural network for the entire day, but maybe you will say, okay, it's maybe better for winter just to estimate the parameter of the model on a winter data set. And maybe for summer, I will use the same model, but with different parameters that I had estimated on the summer data set. Sometimes there's something like that.
Okay, thank you.
Charlotte? No, it was you. No, Charlotte,
yes, yes.
You wanted to ask a question?
J'ai posé ma question. Donc,
Okay, sorry. I thought it was someone else, so it's okay. Okay. I think if you have no more questions, the first lesson is finished. And so now it depends on what you want to do. We can do a short break, like 5 or 10 minutes. And then we can talk about the presentation of the forecasting assignment. And if you don't want any break, we just go now to the forecasting assignment. But if you don't mind,
we can do a break.
Yes. For me, it could be nice if you don't mind to make a short break. So just to take a glass of water. So I will now stop the recording, and then I will put it back for the forecasting assignment presentation. And let's say, so now it is 3:30 p.m. Is it okay for you if we take like 10 minutes? In 10 minutes?
Yes, perfect.
Yes.
Perfect? Okay. So see you in 10 minutes, and in 10 minutes I will record it again for the presentation. So thank you. See you later.